Okay. First, this is sort of a more general announcement beyond the class, since we have signing up going on for both summer and fall, especially for those of you who are GTAs, which I think covers most people here. That be sure to get signed up for both summer and fall. But Sharon has been nagging about paperwork for summer. That's been the main priority right now, but it's just a matter of time before she starts bugging everyone about fall also. So if you haven't been advised, then please be sure to do that. Okay. Other announcement. Regarding quiz 3, this is a quiz on chapter 5. One thing I didn't think about when I was covering that chapter is I didn't really take the time to talk about um, biconjugate gradient and a related concept of bi-orthogonality, not realizing at the time that two of the questions on the quiz are about that. So you don't have to do those questions. If you decide to do them anyway and get them right, then I will throw bonus points your way. So yeah, so I just goof there because I didn't really cover closely the idea of mine that there's, as far as a regular homework assignment, like the actual problems, there are none concerning biconjugate gradient, but I wasn't thinking about the quiz questions. So, oops. Okay, so now continuing with chapter 6 on eigenvalues. What is going on here? Okay. Okay, let's make sure recording is going. Okay. Now, when it comes to finding eigenvalues of a matrix, there were two key questions that were brought up last time. The first is, for what kind of matrices can eigenvalues easily be determined? And then second, how do we take the case of a general square matrix A and reduce it to one of those, such a simpler case? Just like with AX equals B, that's Gaussian elimination. Its purpose is to reduce a general square invertible matrix to one that is upper triangular, because an upper triangular system is easy to solve. Now, we do have a tool in our arsenal for the eigenvalue problem, is that we can use a similarity transformation, and just to refresh your memory. So A is replaced by P inverse AP for some matrix P. So it's overwritten with that, because any transformation of this form gives you a matrix that's similar to A, meaning that it has the same eigenvalues. So we want to keep applying the transformations of this form to obtain some eigenvalue revealing forms, such as triangular. So how do we go about doing that? It's actually going to take some time to flesh out, but we'll get started on that today. Okay. So let's suppose that we have our square matrix A that could be complex, and we have n eigenvector, because the first algorithm we're going to learn in this chapter is one that will, in most cases, give us a single eigenvalue and corresponding eigenvector. Specifically, the largest eigenvalue. So if we have one such eigenpair, eigenvalue, eigenvector, what can we do with it to reduce the size of a problem to get us on the path to finding the remaining eigenvalues and eigenvectors? So lambda is our eigenvalue, x is our eigenvector, and we'll normalize it so that it is a unit vector. It has a 2 norm of 1. So then what we can do is come up with a householder reflection that I'll call P, such that if you apply P to your eigenvector x, you'll get E1, the first column of identity. And we know we can do this because a householder reflection is an orthogonal matrix, or really P might be complex. So P Hermitian transpose equals P. So it is Hermitian is a complex counterpart of symmetric. So P transpose equals P, it's symmetric. PH equals P is Hermitian, which is how things involving symmetry for real matrices normally generalizes to complex matrices. And it is a unitary matrix. So when P is real, we say orthogonal. P transpose P is identity. To generalize in the most appropriate way to a complex case, we say PH times P is identity, and we say P is unitary. So because P is unitary, if I apply P to any vector, the result will have the same magnitude, the same 2 norm. So x is already assumed to be a unit vector, so for any unit vector here, I can come up with a P so that this works. So I can come up with a household reflection P using, let's see, all right. And actually, let's see. There actually is a problem from that section. I don't believe I assigned it. That says, given 2 arbitrary vectors A and B that have the same magnitude, find a householder reflection that maps one to the other. So that's something you can always do. Okay. All right. Okay. Now, one thing that came out of a discussion of householder reflections is a householder reflection is its own inverse. So not only is P times x equal to E1, but P times E1 is equal to x. You can get this from multiplying both sides of this equation by P inverse, which is P. So now what can we do with this? So if I compute PHAP, well, that's the same as P inverse AP due to it being unitary. So this is a similarity transformation of A. So this matrix will have the same eigenvalues as A. But what I want to do is figure out what does the first column of this matrix look like. So to find out, I'm going to take this matrix and multiply it by E1, because this extracts the first column of this matrix. Well, PE1 is equal to x from up here. But x is an eigenvector of A. So AX is lambda x. Lambda is a number. I can put it wherever I want. Now, P is Hermitian, so PH is the same as P. But PX is E1, so I get lambda E1. So now what this is saying is this matrix, PHAP, times E1 is a multiple of E1. In other words, E1 is an eigenvector of this matrix. So, well, what's more important is I have an idea of what this matrix looks like based on its first column. Its first column is just lambda at the first entry, and then all zeros below, and then I have other stuff over here. Point is, this matrix is block upper triangular, and what that tells us from last time is all the eigenvalues of this matrix, which is the same as all the eigenvalues of A, consist of lambda and whatever eigenvalues B has. In other words, I've reduced the size of a problem. So I have one eigenvalue and eigenvector, but by carrying out this process, I've now isolated this matrix that has the rest of A's eigenvalues, and now I can focus on it to find all of them. So what I've just done here to reduce the eigenvalue problem for A to one for B, that's called deflation. Deflation is actually used in another setting that's closely related to eigenvalues, because the eigenvalues are the roots of a characteristic polynomial. If you have a polynomial and you find one root of it, so then you factor out, you remove a linear factor corresponding to that root. Like if you have a root A, you divide the polynomial by x minus A. So now the polynomial has degree 1 less, and now you can work on it to find the remaining roots. That also is called deflation. So any questions about what happened here in this deflation? Now what we can do is keep going. I can then find an eigenvalue and eigenvector of B, and then deflate on B to reduce it to a slightly smaller eigenvalue problem. So continuing this off away to its extreme, I get a new decomposition. It's called the Schur decomposition. A is equal to a unitary matrix Q, or if Q is real, it'll be orthogonal, times an upper triangular matrix T, and then a Hermitian transpose of Q. So, and since T is upper triangular and has the same eigenvalues of A, the diagonal entries of T are the eigenvalues of A. So this is our eigenvalue revealing form. Ultimately, we'll see an algorithm that will produce the Schur decomposition of A to give us the eigenvalues. And any square complex matrix has a Schur decomposition, so it always exists. It's not necessarily unique because the eigenvalues can occur along a diagonal in any order. Or it's possible the columns of Q might be scaled by something. So we don't have uniqueness, but we do always have existence. So for any square matrix, we can try to find this decomposition to get the eigenvalues. Okay. Now we have an easy way to get that in MATLAB. MATLAB provides a Schur function that computes it. So if you do Schur of A, it gives two outputs. The first output is of your orthogonal matrix Q, or unitary matrix Q, and then the second output is an upper triangular matrix T that has the eigenvalues. Okay. Now, I want to point out the behavior of this Schur function when A is real. So if A is a real matrix, but it has complex eigenvalues, then the Schur function does not return exactly the Schur decomposition of A as I've described it. It returns what is called the real Schur form. So in this case, Q is an orthogonal matrix, so Q it's real, so Q transpose Q is identity. T is block upper triangular. So for real eigenvalues, you just have a single diagonal entry. For complex eigenvalues, which have to occur in complex conjugate pairs for a real matrix, you get 2 by 2 diagonal blocks. Now, if you really do want the complex Schur form for a real matrix, you can get it. You just have to add this second argument of the word complex in quotes. And you can also call Schur with only one output instead of two. So if that's the case, the upper triangular matrix T is the only thing returned. So then you get the just the eigenvalues in that case. And you might not find a matrix Q all that useful anyway, because except for the first column, the columns of Q are generally not the eigenvectors of A, unless A is, for example, a symmetric matrix. In that case, it is. The function eig that I mentioned earlier, that will give you the eigenvalues and eigenvectors. Okay. Actually, I want to flip over to MATLAB real quick. Okay. Okay. So I'm going to just make a random matrix here. Oh, actually, format short is enough. And if I look at the eigenvalues of A, okay, so we have a couple of them that are complex, and so two of them are complex and the rest are real. So now, if I do T is equal to Schur of A, so what we find here is this matrix is not quite upper triangular. It's mostly upper triangular, but here there's this 2 by 2 block along the diagonal. So and you notice if you look at these diagonal entries, this one, and this one, these correspond to the three real eigenvalues of A. The eigenvalues of this 2 by 2 block are the two complex eigenvalues you see here. So that's what I mean by the real Schur form. Whereas if I do Schur A and I do complex, now it gives me a matrix that really is upper triangular. So I went ahead and diagonalized this 2 by 2 block. So now we can see both for real and complex eigenvalues along the diagonal. But this takes up more storage because of real imaginary parts, even whenever not needed, like for these entries here. So it's a bit wasteful in that sense. Okay, now flip back to the notes.
Is storage the only reason why you'd use one over the other?
Not exclusively. Also, complex arithmetic. Because, like, for example, and I think I mentioned this in a recent class, complex addition and subtraction costs twice as much as real operations. Addition or multiplication and division 3 to 4 times as much. So algorithms dealing with real matrices, we try to just not do complex arithmetic at all, which is actually one of the major themes in the algorithm development part this chapter, and because what you can do is once you have a real Schur form, you can still get the complex eigenvalues just from that 2x2 matrix in this example, but then you're not having to do complex arithmetic on the entire matrix, which is what happens when you try to get the complex Schur form. Because what you'll see when we develop a QR algorithm for computing eigenvalues, if a matrix is real but has complex eigenvalues, we can still avoid doing any complex arithmetic whatsoever until the very, very end if you actually need those complex conjugate pairs. So, very good question, though. Because it's easy for one to think, well, you can do the complex arithmetic, so what's the big deal? Well, for large problems, if you're going to have double your storage and more than double your arithmetic time, then for large scale problems, that's a problem. Okay. Okay. I mentioned that the columns of a Schur matrix Q are not the eigenvectors generally, but except the first column always is. But otherwise, there's no real relationship, no simple relationship between the other columns of Q, which are also the Schur vectors of A, and the eigenvectors of A. So if you really want the eigenvectors and you compute the Schur decomposition, unless the matrix is symmetric, or belongs to certain other classes, like what's called a normal matrix, you'd have some post-processing to do to get the eigenvectors. And in some cases, with unsymmetric matrices, that could be a pain. Okay. What we can say, though, is if you start at Q1, the first column of Q, and then go up to a certain point at Qj, so you're including the first J columns of capital Q, those do form what's called an invariant subspace of A. So you can, so let's suppose you want the first J eigenvalues, you can work just with these, and find a linear combination of them that would give you eigenvectors. Now, okay, so I want to say more completely, when are the Schur vectors also eigenvectors? I mentioned A is a normal matrix, so what is that? A normal matrix is a matrix that commutes with its adjoint. The adjoint is also the Hermitian transpose. So if AHA equals AAH, which is certainly true if A equals AH, like it's a symmetric or Hermitian matrix, then if a matrix is normal, so then the Schur decomposition gives you eigenvalues and eigenvectors. So a matrix is real and symmetric or skew symmetric. So a matrix is skew symmetric if A is equal to minus A transpose. So those are two examples of subclasses of normal matrices. And what happens in that case is if A is normal, then the normalized eigenvectors form an orthonormal basis for complex n-dimensional space. So if lambda 1 and lambda n are the eigenvalues, and then they have these orthonormal eigenvectors, again, this is a case where A is normal, then the matrix T, the upper triangular matrix, from a Schur decomposition, is actually a diagonal matrix, because a matrix that is upper triangular and normal has to be a diagonal matrix. That's actually one of the homework problems in this section. I don't recall if I assigned it or not. So you actually have this situation where the columns of Q are the eigenvectors of A, and the diagonal entries of D are the eigenvalues. So what this says is, if I multiply both sides of this by QH, I have QHAQ on the left side. QHQ is identity, because Q is a unitary matrix. That cancels, and you're left with D. So what this says is A is similar to a diagonal matrix in the sense of similarity transformations. So whenever the matrix A is similar to a diagonal matrix, in other words, there's some similarity transformation of A that will give you a diagonal matrix, then we say that the matrix A is diagonalizable. So in other words, it's possible to use similarity transformations to make it diagonal, which is great if we can do that, because then the diagonal entries are the eigenvalues, and then your similarity transformation will point you to the eigenvectors. And I can say something further here. In this case, the similarity transformation I used with Q is a unitary matrix. So A is not just diagonalizable, it's unitarily diagonalizable. Which is nice, because then that means that not only does similarity transformation give you the eigenvectors of A, but we also know that those eigenvectors are orthogonal. So what I've shown here is the nice case, when A is a normal matrix, such as a symmetric matrix, where it is possible to use a unitary similarity transformation to reduce A to diagonal form, get the eigenvalues and orthogonal eigenvectors. But what about the not so nice case? Because this is not always possible. So if A is not a normal matrix, then this is not possible. So what happens in those cases? Actually, a lot of complications can happen. All right. So if A is not a normal matrix, it's not unitarily diagonalizable. It may still be diagonalizable. So we have a situation like this. You can perform a similarity transformation involving some invertible matrix P. So it's invertible, it's just not unitary or orthogonal. And we still get a diagonal matrix. And that matrix will still have the eigenvalues of A on its diagonal. So what we know is we have this situation. A times P is P times D. If you just take this equation and multiply both sides on the left by P, then you get this. And so the columns of P are the eigenvectors of A. Also, the rows of P inverse are the eigenvectors of the transpose, which also are the left eigenvectors of A, assuming that the P is real. Okay. Now, I mentioned Eig earlier. Eig, if used with only one output, just gives a column vector containing the eigenvalues. But another usage of Eig, there's two outputs, like you do with Schur. We have XD is Eig A. So X is a matrix that has the columns, which columns are the eigenvectors of A. and the diagonal entries of D. D is a diagonal matrix. Its diagonal entries are the eigenvalues. So if you need both, then this is what do you do for Eig? So then you can say that, except for round off error, that AX is equal to XD. But what I want to point out is you have this relationship. So in other words, you have this. You do not necessarily have this because the matrix X produced by Eig might not be invertible. In the case where A is not diagonalizable. So that's one thing to be mindful of. So you may have this, but that does not necessarily imply this. So if a matrix that is not normal can still be diagonalizable, when does that happen? So first we're going to look at how eigenvectors of different eigenvalues relate to one another. So let's suppose I have two eigenvalues, lambda 1, lambda 2, that are distinct, and then these are the eigenvectors. And now I'm going to assume that these vectors are linearly dependent. In other words, they're parallel. So these are both non-zero vectors because they're eigenvectors. So what it's saying is that x2 is a scalar multiple of x1. So now, if I multiply x2 by a, I get lambda 2 x2. But I can also say ax2 is equal to a times cx1, because that's what x2 is equal to. But ax1 is lambda 1 x1, because x1 is an eigenvector of a with eigenvalue lambda 1. But cx1 is x2. So I have ax2 is lambda 2 x2, and ax2 is equal to lambda 1 x2. But I already assumed going in lambda 1 and lambda 2 are distinct. So that's a contradiction. So this assumption has to be incorrect. Or it has to be false. So what this says is that eigenvectors corresponding to distinct eigenvalues must be linearly independent. And this argument can be extended to any number of eigenvectors. That's actually one of the explorations in this section. To prove, here I did it for two vectors, it can be proven in a more general case. You have any number of eigenvectors of distinct eigenvalues, they must be linearly independent. So if a matrix A has all distinct eigenvalues, all n of them are different, then you have an A has n linearly independent eigenvectors. So if capital X is a matrix whose columns are these eigenvectors, you have this relationship. And since the columns are linearly independent, X is an invertible matrix. So now we have this relationship, and we can say that A is diagonalizable. So any matrix at all, normal or not, that has all distinct eigenvalues is diagonalizable. So at least that's one large category of matrices for which we can make that claim. So what if the eigenvalues are not all distinct? What if we have a repetition? In other words, a characteristic polynomial whose roots are the eigenvalues has repeated roots. Then, so let's suppose that it occurs as a root m times. So it doesn't necessarily mean that that one repeating eigenvalue corresponds to m linearly independent eigenvectors. In fact, the situation is quite murky. So I need to introduce some terminology here. So first, if I have an eigenvalue of a complex matrix, the subspace spanned by all the eigenvectors of A, we call that an eigenspace. Because obviously we don't have enough eigenwords. So what do we know about this eigenspace? First, it has to have dimension at least one, because any eigenvalue has to have at least one eigenvector that goes with it. Because that's literally the definition of an eigenvector, an eigenvalue. Now, very important, if you take a multiple of an eigenvector as a non-zero, that is also an eigenvector. So any eigenvector defines a one-dimensional eigenspace. Sorry, not true. It's not necessarily an eigenspace all by itself, but it is a one-dimensional invariant subspace. If lambda is not a repeated eigenvalue, then that one eigenvector does span a one-dimensional eigenspace. But not necessarily true if lambda is repeated. So a repeated eigenvalue may or may not have more than one linearly independent eigenvector. So however many you have, that's the basis of the eigenspace. So what you can say is any invariant subspace is a union of eigenspaces if a matrix is diagonalizable. So now I need additional definitions. Okay, so normally when we talk about a repeated root of a polynomial, we refer to the root's multiplicity. But we have to be careful about multiplicity when talking about eigenvalues and eigenvectors. So the number of times that lambda is a root of a characteristic polynomial, we call it the algebraic multiplicity. So in other words, if you have a eigenvalue lambda, then the factor in the characteristic polynomial's factorization, x minus lambda to some power, that power is the algebraic multiplicity. And that contrasts with the geometric multiplicity of the eigenvalue. That is how many linearly independent eigenvectors that this eigenvalue can possibly have. So algebraic is about the characteristic polynomial. Geometric is about linearly independent eigenvectors. So these two multiplicities are not necessarily the same. But beyond that, what can we say? Geometric is always less than or equal to algebraic. Also, both multiplicities must be at least one. So what happens if the geometric multiplicity is strictly less? You say the eigenvalue is defective. It does not have as many linearly independent eigenvectors as the algebraic multiplicity would suggest it could have. So if you have any defective eigenvalue, then we say that the matrix is defective too. If the algebraic multiplicity is only 1, therefore geometric is also 1, but we call that a simple eigenvalue. So from a numerical standpoint, we like simple eigenvalues. It's the repeated eigenvalues that that can pose problems for numerical methods. Let's suppose we have a defective matrix. So in that case, you do not have enough linearly independent eigenvectors to make a basis for Cn. So what that means is A is not diagonalizable. So let me put it in writing here. So there's no similarity transformation you can make that would reduce A to diagonal form, because similarity transformation is when you multiply matrix A on the left by some matrix P and then on the right by its inverse. But any matrix that contains all the eigenvectors, linearly independent eigenvectors of a defective matrix, will not be a square matrix. Therefore, or it would not be invertible. So, if we can't reduce A to diagonal form, can we at least get something close to that? For example, block diagonal form. Now, sometimes I continue the discussion through the explorations, which I tend not to include here in the notes, but I want to make sure that doesn't cause an incoherence. In this case, I might need to include them anyway. Let's see. Okay. Okay. So if we cannot diagonalize A, here's what we can do. We get what's called the Jordan canonical form. So any matrix, any square matrix has a Jordan form. So this tells us everything we need to know about eigenvalues of A, eigenvectors, as well as multiplicities of the eigenvalues, both algebraic and geometric. And in the case where A is defective, so it does not have a full set of eigenvectors, it has instead what's called generalized eigenvectors. So what does a Jordan canonical form look like? So it is a similar transformation of A. So we have matrix X on the left, its inverse on the right, and then in between we have a block diagonal structure. So this is what's called the Jordan form of A. So it is a block diagonal matrix. And each diagonal block, called a Jordan block, looks like this. It has some eigenvalue of A on a diagonal, and then all ones on the first super diagonal, so one's right above the eigenvalue, everything else 0. Now, how many blocks do we have? It says P altogether. What does P mean? That's how many linearly independent eigenvectors A has in total. So if A is diagonalizable, then you'd have, as n by n, you'd have n such blocks, and each block could only be 1 by 1, so that Jordan block would simply be the eigenvalue itself. But if you don't have a full set of n linearly independent eigenvectors, then you're going to have some blocks that are larger than 1 by 1. Okay, so what else does the Jordan form tell us? All right. Now, it's possible for one eigenvalue to have multiple Jordan blocks that go with it. So how many blocks an eigenvalue has equals the geometric multiplicity of the eigenvalue. That's because each Jordan block is associated with one linearly independent eigenvector of A. Now, if you take all the Jordan blocks associated with an eigenvalue and you add up their sizes, that's the algebraic multiplicity. Okay. And as I mentioned earlier, if A is diagonalizable, each Jordan block is 1 by 1. So the diagonalization of a matrix that gives you all of its linearly independent eigenvectors and eigenvalues, that's a special case of a Jordan form where you only have these trivial Jordan blocks. Okay, so now I'll show you an example. All right, so here's a sample Jordan form of a matrix. So we have the matrix itself is 6 by 6, but because there are 3 Jordan blocks, there are only 3 linearly independent eigenvectors. One for the eigenvalue 2, a second one for the eigenvalue 2, and then one for the eigenvalue 3. But there are 2 blocks associated with the eigenvalue of 2, and you add up their sizes and you get 4. So the eigenvalue 2 has an algebraic multiplicity of 4, the sum of the sizes of the blocks, and then a geometric multiplicity of 2, because there are 2 blocks that go with it. Whereas for the eigenvalue 3, it has an algebraic multiplicity of 2, that's the size of its one and only Jordan block, but its geometric multiplicity is 1. Because there's just one Jordan block associated with 3. So this matrix is really defective because it's 6 by 6, but there are only 3 linearly independent eigenvectors. So in the Jordan form I wrote above, X, the matrix X, has columns that are either eigenvectors or generalized eigenvectors of A. So the columns of X that correspond to the first column of a Jordan block, those are eigenvectors. All other columns of X that correspond to these kind of columns of a Jordan block, those are called generalized eigenvectors. So what that means is AX is not lambda X, but A minus lambda I to a power times X is 0. So that's what it means to be a generalized eigenvector. So between eigenvectors and generalized eigenvectors, you can form a basis for your whole space Cn. Because you can build up enough linearly independent eigenvectors or generalized eigenvectors that way. It's just that it doesn't consist of all eigenvectors. You need generalized ones to complete the set. So questions about a Jordan form and what it means. The Jordan form is quite troublesome numerically. In fact, it's not advised to try to compute it using numerical algorithms at all. The reason why is the eigenvalues of matrix A are continuous functions of the entries of A. So computing eigenvalues by some means is numerically tractable. But a Jordan canonical form is not a continuous function of the entries of a matrix. Now, why is that? Suppose you have two eigenvalues that you compute numerically and are nearly equal. And what if the eigenvectors that go with them are nearly parallel? Because of round-off error, it's impossible to be certain as to whether you really do have two distinct eigenvalues that just happen to be very close. Or maybe they are a repeated eigenvalue, and then you only have one linearly independent eigenvector. Now, whichever one of those situations it is, drastically affects the form of the Jordan form A, because what can happen is if you consider the eigenvalues distinct, that's two 1-by-1 Jordan blocks. If you consider them repeated eigenvalues that have one linearly independent eigenvector, that is a 2-by-2 Jordan block, and a 1 suddenly appears in the matrix, whereas otherwise that would be a 0. So in other words, a slight perturbation of A could lead to an entry of a Jordan form changing from 0 to 1. So that's what I mean by the Jordan form not being a continuous function of the entries of A. That if you have that kind of an abrupt jump, basically literally a jump discontinuity in the entries of the Jordan form, then you do not have that continuity. So anytime you're trying to compute some function of a matrix that is not a continuous function of the entries, it's folly to try to compute, just because you can't really trust your answer. Now that doesn't mean Jordan form is useless, because of and actually discussion later in the section. What I mean by that is a perturbation theory, which actually, am I covering that? Let me check. Oh yes, I do spend some time on that on Wednesday. That when you have eigenvalues that are clustered or repeated eigenvalues, and you're trying to compute the Schur decomposition, that having an understanding of the Jordan form of a matrix can help with analysis of the sensitivity of a problem of computing eigenvalues and eigenvectors, especially of defective matrices. So it still has a purpose from a theoretical standpoint. But actually, I'm curious if MATLAB even has a function for Jordan form. It does in the symbolic toolbox. Let's see if it'll take me to it. Oh. I'm looking at the help page. Yes, so there is a Jordan function in MATLAB that there's an advisory that says that because a Jordan form of a numeric matrix is sensitive to numerical errors, it's best to convert numeric input to exact symbolic form. So in other words, trying to compute a formula for the eigenvalues and also a Jordan form. So that way, round-off error is taken out of a picture. So very And I don't know if researchers have tried to come up with a practical numerical algorithm for computing the Jordan form, but it's something where you basically have to make this kind of determination. If you have eigenvalues that are very close, do you declare them to be repeated eigenvalues or distinct eigenvalues? Because that drastically affects the form of your result. But so personally, I feel like it's just not reliable. Okay. That brings to an end today's notes. Anyone have any homework questions? I know our homework is a ways back from this material, but whatever you got, we do have time.
I have a question.
Yep.
On exploration 5.2.4, I'll let you pull that up.
Yeah. 524.
Mm-hmm.
Okay. Okay.
Do you have any recommendations on how to choose tolerance, the last input?
Oh, a typical value that I choose for tolerance is like 10 to the minus 8. That's deliberately chosen to be the square root of round off error in our floating point system, which is in neighborhood of a 10 to the minus 16. Just because setting a smaller error tolerance may be difficult to achieve it, just because of you're dealing more with round off error at that point. But something like a little larger, like 10 to the minus 8, seems to work well. Or if you try that and it's taking way too long, I can see trying something a bit larger, like 10 to the minus 5.
Okay. So just literally enter that as my input, 10 to the negative 8 or 10 to the negative 5.
Yeah, and in MATLAB syntax, you could do like 1e minus 5 for 10 to the minus 5.
Okay.
Like scientific notation.
Okay. Thank you.
Yep. Okay. Any other? That's fine. I want to get out of here too. Or it gives me time to rest up for PDEs. Okay. So I will stop recording at this point. Of course, if anyone does want to ask a question after others have